Okay, let's work our way around the cycle to understand the states, knowing that all of these control volume devices are governed by enthalpy change of the fluids. We know this by applying the first law to each device from lectures on last week, Wednesday and Friday. Okay, let's start with state 1 and work our way through the cycle. I'm going to clear some space here, but you have the image to refer to. State 1, I know the pressure is 100 bar, and I know the temperature is 480 degrees Celsius. I have two properties that are independent to fix the state. So I can go to tables, or I could use software such as Fluid Prop, and I can determine the enthalpy, 3,321.4 kilojoules per kilogram, and then I can go ahead and grab my specific entropy as well, 6.5282 kilojoules per kilogram Kelvin. Okay, state 2 I can find using state 2s, which is isentropic performance of the turbine, and then I can also use the isentropic efficiency equation. Let's do that. State 2s, I know that the pressure at state 2s is equal to 7 bar. And I know that the entropy at state 2s is equal to the entropy at state 1. I have two independent properties. I can go to the tables at this point, and I can find that my enthalpy at state 2s is equal to 2,684.8 kilojoules per kilogram. Okay, state 2 now I can find from my isentropic efficiency equation. I know that the pressure at state 2 is still at 7 bar, and I can find the enthalpy at state 2. Again, this is just coming from the isentropic efficiency equation. And in this problem, the isentropic efficiency of the turbines is given as 85%. And so plugging and chugging with the numbers, I end up with 2,780.29 kilojoules per kilogram. Okay, state 3, I'm still at 7 bar, my intermediate pressure, but I've gone through reheat back up to 480 Celsius. So I know pressure at state 3 is still 7 bar. I know temperature is 480 degrees Celsius. So I could either go to my superheat tables or use my software and find my specific enthalpy, 3,438.9 kilojoules per kilogram. Specific entropy, 7.8723 kilojoules per kilogram degree Kelvin. Okay, state 4s, I know the entropy and I know the pressure. So the pressure at state 4s is 0.06 bar, and the entropy at state 4s is equal to the entropy at state 3. So I have two independent properties, and I can determine the enthalpy at state 4s, and that should be, I believe, 2,425.6 kilojoules per kilogram. Now I can find state 4. I know the pressure at state 4 is still 0.06 bar, and I can use the isentropic efficiency equation, knowing that's given in the problem, 85% for the turbines. And plugging and chugging, I get to 2,577.6 kilojoules per kilogram. Okay, I'm getting close at this point. I'm going to come up here, get some space. State 5, that one's pretty easy as far as easy thermodynamics goes. The pressure is 0.06 bar, and the quality is 0. It's saturated liquid. So I can go to the saturation tables and get state 5. The enthalpy is 151.53 kilojoules per kilogram. And then I need to work around at this point to get state 6S and then state 6. Oh, give me 1 minute here. Yes, indeed. This would also be a good point to go ahead and grab my let me erase that. Specific volume at state 5. That's equal to 1.006 times 10 to the negative third meters cubed per kilogram. There we go. Okay. So using that, now I can go to state 6S, the isentropic output of the pump. Now remember, the pump is a pressure change device, and so we have to use the first law for a control volume for reversible systems. And we see in that case that the enthalpy at state 6 is approximately equal to the enthalpy at state 5 plus the specific volume at state 5 times the pressure change. If you're confused on this, look back at the notes from the last class. The specific volume, assuming a incompressible substance, times the pressure change, comes from the reversible work of a control volume. I have to do property evaluations, and then I also have to worry about unit conversions. I'm not going to spend time doing that. You should be able to. And I find that state 6S, the enthalpy is equal to 161.59 kilojoules per kilogram. Okay, and then finally for state 6, I can use the definition of the isentropic efficiency for a pump and find that the enthalpy at state 6 is equal to the enthalpy at state 5 plus, now note the slightly different structure because the isentropic efficiency of a pump is flipped from that of a turbine. We have to put more work into a pump to overcome the friction and heat transfer and other irreversibilities. For this problem, the pump efficiency was given as 82%, and so plugging and chugging, we get 163.8 kilojoules per kilogram. Okay, now at this point I have state data for all 6 states. I have enthalpies for all states as well. So I'm in a good position now to calculate the performance of the cycle.